All right, welcome everyone to the latest Trees Around the Globe Student Research Campaign webinar. This is the State of Trees, September 2023. And it's fun name, the Data Escape Hatch, looking at data and how data fusion can help us understand our local to global environments, including a featured discussion on the data fusion of USFS GEDI Old Growth Forest research. Today is Friday, the 8th of September, and you do realize, of course, that this is being done on a day that we usually don't do the webinars, but we had to switch some things up this month. So I'll also mention that this is the last webinar for year 5 of the Trees Around the Globe Student Research Campaign. And we will be starting year 6. We were approved for year 6, and that starts on 1 October. And I have some information about a webinar, the next webinar coming up in a couple minutes. But a little bit here. I'd like to start off the last couple webinars with a nice little quote that I found. I find a couple quotes here now and there, ones that I hear and I look it up to attribute it to whoever said it. But try to have a nice feel with has something to do with trees or forests or land cover, or green up, green down, carbon cycle, things like that. I thought this was an interesting quote. I'm always astonished by a forest. It makes me realize that the fantasy of nature is much larger than my own fantasy. I still have things to learn. I just thought that was a very nice quote to start off this webinar with. Get us thinking about looking at forests, and we're going to be talking about forests here with GEDI and the U.S. Forest Service collaboration and the data involved with that, with our featured guests here today. So with the agenda, as you know, I'm going to do some introduction and some campaign metrics. Going to mention a little bit about what's going on with the NASA Moon Trees Quest happening right now. And then we will pop into our featured presentations. And the first one will be it's Dr. Ben Poulter and Dr. Calle, and Dr. Leo Calle will be the one who is going to be doing the majority of the presentation. We will then follow that with a Q&A with Peter Falcon. And then the next presentation will be with Peder Nelson, looking at data, documenting data, data software, data fusion, and data issues. So all about data, because we, as you know, with the last webinar, we talked a lot about, the synchronization of data. We talked about the harmonization of data. We talked about using different data sets, from ground-based science to space-based science, and how we can tie that all together using online tools, using the Globe database, going out and taking observations and, looking at things from different angles in order to get answers to, a specific, specific question or questions. And then we will have another Q&A with Peder Nelson, with Peter Falcon, and then we will end the meeting. And then that will formally end the last webinar of year 5. So, I also want to say thank you all so much for being part of this campaign, and we look forward to for the year to come. So here we go. This is just this announcement. I showed this last time. We're super excited that we were approved for another year for the campaign, and this was approved by the Globe Program Office at NASA headquarters, as well as a Globe Implementation Office in Boulder, Colorado. So they came together. I pitched what we wanted to do. Peter Falcon and I talked to some folks at the Globe annual meeting in Denver in July, and then they gave us the go ahead, and I just submitted some information to them about some of the things we have planned for year 6 of the campaign. Now, with that said, I also want to mention that we will have our first webinar, and our team is going to be building this webinar a little bit better next week, but I had to get this information to the Globe Program Office. But as you can see, we've changed the tree here with the leaves hanging down. As you know, the leaves are the numbers of the years. So we have year 6 coming. And on the 10th of October, which is a Tuesday at 1 p.m. Eastern Time, we will have the State of Trees, October 2023, the start of year 6, aligning to the Globe Year of Climate and Carbon, or also known as the YCC, through Globe tree height, land cover, greenings, and carbon cycle data, and a global student and campaign collaboration. So Grace Crane Wright of the Globe Implementation Office, she will be the featured presenter at this webinar. So, stay tuned for this. You will see, I will send out later today, I will send out an invite via Outlook for you to put in your calendar. So stay tuned for that. Now, before we move on to the feature presentations, I also wanted to announce that ISET 2, as you know, the Ice Cloud and Land Elevation Satellite 2, or ISET 2 mission, is a huge part of our campaign because we started the campaign the day of the launch on 15 September 2018. So on that date, next week, we are celebrating ISET 2's 5th anniversary in space. Okay, there's the website for it. Well, we're super excited about that. But one thing I want to show you is some numbers we just came up with literally earlier today, is that since ISET 2 was launched on 15 September 2018, there have been 4.68 times 10 to the 26th, or 4.68 septillion photons released by Atlas instrument on ISET 2. Now, a little background to how we got that number. So as you know, ISET 2 fires off approximately 10,000 laser pulses per second. And each laser pulse is approximately 300 trillion photons. The latest number, and this was as of earlier this week, was just over 1.5 trillion laser shots. And if we take the 1.5 trillion laser shots, multiply that by that average of 300 trillion, this is what we get, an insane number, one that's not even fathomable. Okay, now, I should also mention, though, as you know, this does not mean that we have 4.68 septillion measurements of height from ISET 2 or the Atlas instrument on ISET 2. If you remember, we get an average of about 12 photons returned out of that 300 trillion photons from ISET 2. So the number is going to be a lot smaller. It's still in the trillions, but we have trillions of data points from ISET 2. But this is the number of, the estimated number, of course, not exact, estimated number of photons released by the Atlas instrument. And if you remember, Atlas is the Advanced Topographic Laser Altimeter System. It's the instrument, the laser altimeter instrument on board ISET 2. So nice, huge number to start your weekend, this week. So as you know, I show this every time. I update this right before we have the webinar. But yeah, draw your attention to the bottom, year 5. And remember, that started on the 1st of October of 2022. And we have lots of observations coming in. We have over 38,000 observations coming in from over 11,000 global sites. So since the campaign began, we have over 163,000 observations of tree height, land cover, and green up, green down, or greenings from all over 54,600 global sites. So we're super excited about that. And also stay tuned to the Globe page, the Globe Observer page. I wrote a blog that covers like 5 years of the Trees campaign, 5 years of ISET 2, and that's going to be put up probably later today by folks on our team. That's going to be up there under the news section of the Globe Observer. I didn't include a link because it's not actually up there yet. It may be as I'm speaking. But check that out because it's a blog that I wrote, a Globe Observer science blog, being the tree science lead for the Globe Observer. I created this blog to parallel 5 years of the Trees Around the Globe Student Research Campaign and 5 years of ISET 2 in space. Basically, the last 5 years of looking at trees from space. All right. So, oh yeah, last thing here before I move on to introduce the feature presentations. As you know, right now we have going on the NASA Moon Trees Quest, and we only have 13 days left for folks in the United States to submit tree height observations of one moon tree species, and these would be the Douglas fir, loblolly pine, sweet gum sycamore, and it says giant sequoia here. This is what was on Artemis. On Apollo 14 was Coast Redwood, and as you know, the Coast Redwoods were switched with their cousin giant sequoia for Artemis because giant sequoias have a larger geographical distribution than the Coast Redwoods do. So if you're doing this, if you're taking part of this quest, you have 13 days left. This will end on the 21st of September, and you will stop seeing the pop-up on your app if you have it open. If you've seen the pop-up, if you're in a location, in one of the locations where one of these tree species is found, found or highly populated. But then also, as part of this quest, if you have access to find one of the actual planted Apollo 14 moon trees, And as you know, on the website here listed, we have all those listed there, where they are and how you can access them with their lat longs, their addresses, and everything. We have, over 80 of these trees and tree species that have been identified already, through this quest. So we're super excited about it. And since we began the trees quest, globally, we have almost 5,000 tree height observations around the world. Okay, of course, not just because of the quest, but it seems like this might have sparked an interest in folks to get out there and do tree height measurements, even though they may not have access to any of the moon trees. So I just wanted to highlight that. So with this moon trees quest, okay, this was I want to bring the slide up because this is we have 5 reels that have been put out on social media on the GLOW program, whether it be the GLOW program, the Artemis mission, the USDA Forest Service, and the NASA uh, uh, Office of STEM Engagement Next Gen STEM program have all posted about the Moon Trees Quest. And we have all created reels. We have collaborative reels that some were put up by Artemis, created by Artemis, put out by Artemis. Some were created by the USDA Forest Service. Others were created by the GLOBE program and NASA. So we have over 500,000 views of these 5 reels. And I'm just going to play this brief one here. This is the latest one, and you should all know who this is here. You've most likely met her. A lot of you have, I should say. This is Jennifer Bourgeot, but let me just play this reel here. It's about a minute long, but this is the latest reel for the quest.
I am Jennifer Bourgeot, the GLOBE Program's United States Country Coordinator, and I'm here in this wooded area of New Hampshire looking for a sycamore tree so I can join the Moon Trees Quest before it ends on September 21st. Although I'm having fun with the quest, I'm really looking forward to what comes next, when you propose to host your own moon tree.
That's right, Jen. Educators and students based in the United States will be able to apply to host a moon tree. The GLOBE program offers many tree-related protocols and resources that can help educate those interested in applying. Back to you, Jen.
We have some ideas that we pulled together for you. We posted them on our website to make it as easy as possible.
What's cool about that is you can then go on to you can go into Artemis social media and find out where you can, if you're in the United States, apply to host a moon tree, because they have been germinated and they're growing right now in several locations across the U.S. in some nurseries, so some academic nurseries. So Artemis are the people who are running that, and the USDA Forest Service is running the growing of these Artemis moon trees.
I am.
So with that said, I'm going to introduce I have 2 slides here, then I will pass it over in a second. Actually, I have one little quick video here. But we have 2 presentations today. The first one will be U.S. Forest Service and GEDI Old Growth Forest Research, Dr. Ben Poulter and Dr. Leo Calle. I believe Dr. Calle is going to be the one who's going to be presenting today. So we're excited about this, to see this kind of data fusion that we've been talking about over the last several webinars, the last several months with the campaign. So we're excited about that. And then following that, we will have Peder Nelson. He will be talking all about data and looking at that Z dimension of height. So before I pass it over to you, Dr. Calle, I'm going to quickly pop this, and I hope this doesn't steal any of your thunder. It's just a quick video. This is a promo video that GEDI put out just prior to launch back in 2018. But this is to show you exactly what it's doing, and then we will learn from Dr. Calle a little bit about I should say a lot about the old growth forest research and this kind of this data fusion between GEDI and the U.S. Forest Service. So let me go ahead and play this. This is relatively short here. So, and then I'll pass it over to Dr. Calle. I just love the music in that one. So, in the past, you've learned a bit about kind of the generalities of the Jedi mission on ISS, but today we're going to, have a little bit more of a focus. So, Dr. Kaye, I'm going to stop sharing and I will pass it over to you right now.
Okay, I'll start sharing.
All right. Thank you so much for agreeing to do the presentation today,
Yeah, for sure.
because everyone here
Sure.
is super excited about anything tree height, forest related. That's just what our campaign does. And we have a great group of folks here, and it looks like from close to 10 countries are here right now.
What are moon trees? Well, I get this set up.
Yeah, so the Apollo 14, 1971, astronaut Stuart Roosa took about, a couple thousand seeds around the moon, and they brought them back to Earth, and they were germinated by the Forest Service, and then they were planted all over the United States and some in South America, and a lot of those are growing still today. And Artemis just on Artemis 1 to the moon, around the moon, came back. They took another, whole, couple thousand seeds, uh, a trip to the moon, and then back again. And these are being germinated now. And so basically, they originally started doing this to look at any type of radiation effects that, would have being in space would have on the seeds, and the trees, and would they grow differently than than trees that were just grown normally on Earth. So they're kind of paying tribute. The Artemis mission is paying tribute to the Apollo 14 mission and Stuart Roosa's idea of taking these seeds to space and bringing them back and having these trees grow and seeing if they grow any differently than trees just grown on Earth normally.
Cool.
Oh yeah. All right, that looks good on our end.
Okay, great.
Yep.
Thanks for having us and letting me talk with you guys. I'm based out of Missoula, Montana, but I work for University of Maryland, ESSIC, and I'm funded through NASA contracts. And one of them is to work on this mature and old growth mapping project. I started on this project in February, but it was really initiated last April or 2022 on Earth Day from an executive order that recognized really that there was value in classifying, inventorying, and protecting mature and old growth forests, not just for their carbon benefits, right? Old growth forests or forests that are older typically have certain structural characteristics. They also have societal values, cultural values for recreation, and otherwise, but they also bigger trees, lots of biomass, lots of carbon stored. And it was a mandate for the agencies to classify the forests, right, and categorize them into what is typically thought of in forestry as a continuous state of succession. And why we think old growth matters is varies from group to group, depending on their own perspectives. Ecologists are classically thinking about serial progression of young to old forests and the complexities associated with biodiversity, habitat, and other types of societal values will also inform what is considered an old growth. An old growth forest in the Pacific Northwest is very different from an old growth forest in the East Coast, where disturbances are different. The characteristics of the environment and the growth status of the plants growing there create different structural properties and also characteristics of those forests. And the definition itself, imposed by this executive order, made things quite complicated, because to that point, the community really hadn't been required to really classify the states of maturity of forests. And putting a definition on it really goes back to how do you enforce protection? How do you enforce management of different states of forests? So it really informs policy in a lot of ways. And these maps that we're going to generate, the US Forest Service, NASA, and others, of where the inventory of mature forests are located, where they, who's managing them, and who's required to maintain them, protect them, monitor them. The middle figure is a conceptual diagram of what different states of forests might look like in different types of systems. This is by U.S. Forest Service colleague Chris Woodall, who works with the Forest Inventory and Analysis Program of the U.S. Forest Service, and they're characterizing, classifying different systems into mature and old growth and young cereal states. But one can also view the state of the forest from a carbon perspective. This is on the right side. The right image here is a figure from Kevin Barnett's paper earlier in 2020, earlier this year, that kind of thinks about it from a functional perspective. When is a forest old, right? Is it old when it stops accumulating carbon? That's their perspective, right? And it makes a lot of sense to a lot of degree, depends on what you're managing and what you're monitoring the forest for. Forest trees will accumulate carbon, but after some time, they're going to asymptote in terms of the density that's on the land. And if we're viewing old growth and mature forests from the perspective of carbon climate benefits, that seems like a valid perspective. But it can't be the only one, because there are more stakeholders involved and other interests involved than just pure carbon standpoint. Looking at it from a different perspective, going and hitting the same themes, is it structure? Is it function? What is old growth? And it leads to kind of different maps of where mature and old growth are. It's not just, it could just be age, right? That is one simple measure that's imbued in the name of old growth and mature. But there are other characteristics. De La Sala had created a data set that was informed by total biomass on the lands, the average tree heights of those trees in a pixel, right? How much plant cover, tree cover is there in a certain pixel, using those kind of structural characteristics to inform a classification of young, intermediate, and old growth. And Barnett's paper kind of takes it down into a functional definition of old, right? And these are evolving, right? These are evolving definitions that really need to be narrowed down, and because they will be the definitions that inform policy, that inform decision making on how to manage and monitor the lands that we're going to classify effectively. And so that is relevant, and I don't think that there's a lot of discussion right now going around in the literature and in the public sphere of just science debate, right, about how we fix or make flexible these definitions for moving science forward. But I think the consensus is generally like there is less old growth than there used to be, right? There's a depiction of what old growth or virgin forest, right, might have looked like a few hundred years ago to where it is today, influenced by logging, land use change, fire disturbances, natural disturbances. But the bottom right image of where primary forest is today is pretty consistent with what we're seeing out of the data estimates from upscaled projection from FIA, which is field-based plot level data that are used to classify field plots and then scaling it up in terms of fraction. Where is old growth now? And the map that you've seen on the bottom right is an estimate from April, an early estimate that's since been revised to include some BLM land and other federal land that's being managed. You might not see all forest here depicted on the bottom right. And this is strictly federally managed forested land that's being depicted in this map in the bottom right, because that is that follows the mandate from the executive order of what should be managed, needs to be managed, and needs to be inventoried. So this is a complex figure on the left here, but it's from Walker of last year, and it's thinking about this space of why is it important? Why is old growth and mature forest important? On the y-axis here, you have potential carbon storage, and on the x-axis, you have current carbon storage. And so if your potential is always going to be higher or equal to your current carbon storage, right? And so when you have high potential on the y-axis and low carbon storage, that means you have a lot of potential to protect and allow those ecosystems to accumulate carbon. Old growth carbon lives along this diagonal, really. It has high amounts of biomass, high amounts of carbon in the land that is close to the current stocks of where we have, right? And so if we weren't to protect those and they were to get logged or disturbed, you transfer a lot of that solid carbon into gaseous carbon or other forms that that prevents the land from providing this like natural climate solution of just carbon storage, basically. And there is benefit to allowing younger forests to mature, where they have high potential carbon storage, but low current carbon storage because they're young. But as you allow them to mature, your management of those lands will differ, right? Do you want to maintain and manage, or you want to maintain and protect and monitor? And this is very much a carbon and also a functional perspective of trying to identify those locations of where is mature on the lands, where is old growth, how close are those ecosystems and forests to their potential maximum of carbon storage, and where do we need to protect in terms of just having an idea of where they are on the land. Moving forward to how we measure forests, it's the U.S. Forest Service, starting with that, primarily uses the Forest Inventory and Analysis Plot Network. And the managed land of national forests is in this top left, with some that also includes, it's primarily U.S. Forest Service. So there is more forested land than what's depicted here, but the plot networks of the sample plots, they sample of area approximately 2,500 square meters, about an acre for one forest inventory plot. And it's every 5 kilometers that represents each plot and sampled area will represent a 25 square kilometer area. And the plots look like what's looked on the bottom left. So they'll go out in the field and they'll measure in these subplots around this. All of these subplots are considered a plot. It's a very statistical design of generating uncertainties and sampling the land and projecting those estimates to a larger area. And they're unbiased, they're systematically distributed plots across the forested lands and grasslands. But they don't, on the footprint basis of observations, it, it they really measure like 425 to 1,000 square kilometers of an area. That's where they're getting observable information from the ground, right? So they'll measure tree heights, they'll core trees, they'll measure stems on the ground, how much litter. They'll measure. They'll revisit the pots every 5 years. And they'll get ground truth measurements, right, from that you can hold in your hands. But the footprint of where that information is coming from is very small compared to the total forested area. And this is particularly relevant for why we got involved in terms of the GEDI group, because there is recognition within the U.S. Forest Service and outside that you need more information on the land than just the sampled area, simply because of the footprint of where that information is coming from is just much smaller than, and it's harder to retrieve in that field data. And that's a point I want to emphasize, and I want to make sure that it's understood well. This is the old growth criteria that they're using. And Kristen Pells has put out a paper that's being submitted. It's public in terms of like the document. So I'm sharing it here. But what you'll see is that there's different criteria for old growth in different regions, right? And so for the southwestern region, where it's quite dry, the trees might not reach a certain height over time. It's going to be slower, right, growth, but it's still considered old growth, but there's different criteria. And that's same for other regions, right? And so this is something that came about in their understanding and our understanding of what is mature, what is old growth in these different ecosystems that are under different climatological, environmental drivers of growth and state. So how can remote sensing help? How can NASA help? And this really just leads back to like a history of getting Earth observations slowly but surely, ramping up in 2000s and really starting with like Landsat in the 80s, but progressing to what seems just like ever increasing satellite observables about the Earth system and about ecosystems, both structure from or optical sensing, hyperspectral reflectances of lands and depictions of how the land is changing, to 3D vertical observations from photon returns, from LiDAR, from radar, and getting different verticality to that information and depth of information that we're retrieving about ecosystems and their structure and function. If you're not already familiar, I wasn't too aware of the GLOBE program, but I put this on there for those that aren't too familiar with the DAC network, which is changing and evolving into something new. So it might not be called the DACs in the future. It might be called something else. But the point being that there are a few repositories where I typically go to for forest ecosystem data. And these are highlighted in the LPDAC, Oak Ridge, and CDAC for sources, data sources related to forests and ecosystems. Okay. So bringing back and coming to GEDI, right? It was a long history, but finally it got launched in December 19, started producing data. It's on the ISS, on this this module of the ISS, and it's been taken down in March, but it's going to be relaunched in 2024. I think it going through 2028, 27. That's the anticipated timeline for future retrievals. But I wanted to also show this, and I'm hoping that it works well and the sound comes through. It's a minute.
USGS, Science for a Changing World, in cooperation with NASA.
So it's a little bit the same, but it's different imagery than what you saw with GEDI.
On the International Space Station, 254 miles up, orbiting once every 90 minutes, GEDI uses waveform LiDAR to record elevation and canopy data. 3 lasers split into 4 beams, firing 242 times per second, are dithered to 8 tracks 600 meters apart, with 25-meter footprints every 60 meters. That's 968 footprints per second. Laser energy traveling almost 300 million meters per second reflects off higher surfaces first, then lower surfaces shortly after. The tiny delay is detectable by GEDI's telescope sensor, which records the intensity of the reflection over time and uses the known speed of light with other variables to calculate a waveform, documenting the reflective density of the footprint at various elevations, representing the surface below. Users can process these data into maps illustrating ground elevation, canopy height, and other surface characteristics. What's new in version 2? Suborbit granules, spatial metadata, improved geolocation, best algorithm by default, and data layer updates and additions. GEDI version 2 data products, available now.
That was a pretty good advertisement. But and I'll stop it there. But moving forward, what I want to emphasize is that, like, on a cross section, if this was a forest, right, this is the depiction of density of the photon returns. So you'll have high density on the ground, which might be represent some micro topography in the land or some potholes, what have you. But you also see vertical structural information that could be translated into these volumetric estimates of plant area volume as a function of height on the track. So this is a NASA scientific visualization studio created this image that you're seeing here, where it says GEDI tracks of the plant, of translating that data of plant area volume, which is really a function of the waveform that we're seeing, into vertical approximations of where the mass, or where the majority of those photons are returning as a function of height from the ground elevation. And so this translates to, like, the work now that we're doing, and one of the things that's been used is a quick and easy way, right? That when people started using the GEDI data, they got the canopy height, right? They got the 98th percentile return from that waveform. Meaning, if this is the depiction on a cross section, you might see this as, like, this is almost the top of the trees right here, near the background noise, right? This is the ground data, the last peak on the return. And what people were using the canopy or the GEDI data for was just a canopy surface model, canopy height model. And so when we came into this, and there's other folks who've been using these other kind of statistics from the full waveform, but there is more structural information than what's typically been used to build biomass models or to build other types of information that can inform some classification. But the biomass models have been quite successfully used. This is a paper just put out by James Bruning with Ralph Debaya. James is a PhD student, but the work that he's done primarily on GEDI has been training GEDI-based models using FIA co-located data to build out these GEDI-based biomass models, which can have greater spatial coverage to provide that information for users. What we're doing now, what I'm doing as part of the work for the MOG for mature and old growth mapping, is really thinking about the information in GEDI across the full waveform. And so we're thinking about it from an unsupervised classification perspective. And the first one being is there differentiable information in populations of waveforms if you look at the landscape level? On the left side is a cluster analysis result showing a pretty large domain, what the U.S. Forest Service calls firesheds. And we're taking all of the waveform statistics, so not just that top of canopy height return from GEDI, but taking all the structural characteristics that are returned from that LiDAR pulse and that footprint to classify, to see if there is natural groupings of unique structural groups in the landscape. And here we can identify 4 distinct structural groups that differ along some, not just the how tall they are, but some structural differences within the top of the canopy to the bottom of the ground. And we could look at this in different ways, right? And right now we're exploring how we're looking at attribution of group membership in relation to classic ecological forest ecology drivers of growth and structural changes. So how does structure group membership differ as a function of topography, edaphic conditions or soil, climatic differences, and land use history? And where our intent is to come back to this group membership and look at and try to compare and identify if FIA, so ground level plots, once classified using ground-based type of criteria, do they fit into these natural clusters of the GEDI data? And the overarching question is really, what is the differentiable information in GEDI that can inform some higher level mapping? And we want to do characterization and attribution of these clusters, like I said, and looking at differences among average climatic variables, soils, topography, aspects, slope, elevation, topographic position. But looking at these plots on the bottom right, on the far right, there's above ground biomass density on the y-axis and relative height 98. So the tallest part of that canopy, effectively, you have some clustering into certain groups where there's high above ground density and also high relative heights. And you get some flip-flop of some of these classes and structures of groups where in purple, they would have high above ground density, but relatively lower relative heights than maybe say the green cluster. But when you look at the intermediary measures of structure, where the 70th percentile of height against versus the 20th percentile of heights, you have some different types of structural information that's being presented, and that's being captured by the analysis methods. It's being able to distinguish below canopy structure from that GEDI data. And one thing that's come out so far is that there, among different firesheds, there's different structural groupings and there's different characteristics that are just being identified, right? In one cluster, statistically, there can be many distinct structural groups of forests, according to the GEDI and LiDAR data. There can also be clear features that are evident in the landscape. And it's at this point in time, it's unclear, but it clearly looks like, to me, there are striations in the purple group, for example, that may or may not follow some landscape feature, might follow an aspect or a ridge line and aspect, for example. But this is something that will come out later in the attribution analysis. And there's also some spatial separation of these groups that are more distinct. This checkerboard pattern that is seen in this fireshed are gaps, not not because there are gaps in the data, but mainly because there are gaps in the managed lands. Is it public, federal, private? Who manages it? And this checkerboard pattern is classic of logging, clear-cut logging, and allocations for land management. But it has distinct features in terms of their structural groups that are being evident in the LiDAR data for this fireshed. We're also using the GEDI waveforms themselves to kind of build out these predictions of old growth forest, training on the US Forest Service-based maps to see how well the GEDI-based models can inform mature and old growth mapping in the absence of FIA data. The entire objective and goal is to try to integrate GEDI data into the inventorying process, because field work is hard and it takes long. And we want to build a monitoring network that can be readily updated. And we see that, and the US Forest and NASA both sees that as something that satellites can provide, and can supplement the ground-based efforts that are costly and just take longer time in terms of monitoring the inventoried lands for mature and old growth. Next steps forward, we do have a field campaign plans with Neil Peterson and Harvard Forest to sample, to collect field-based samples of forest structure along the GEDI footprints themselves in known old growth forests, to kind of help build our models and to validate them. And we want to align the measurements that we're generating on the ground to match in some ways or another what GEDI can see versus LiDAR, right? The vertical complexity that's being generated by the GEDI waveforms, which the GEDI footprints do not always align with the forest inventory and analysis plot network. There are specific satellite tracks where measurements are made, and they just don't always align with the FIA plots, which makes a joint analysis of GEDI and FIA a little bit complicated due to reduced number of samples that we have to generate the models. And there is also the limitation of being able to use FIA plots because their coordinates are fuzzed when you download them. That's it's a congressional mandate to scrub or fuzz the coordinate locations to protect privacy of when and where those FIA plots are located. There is a next step to this effort of inventorying. It's a threat analysis. It's being led by Ray Davis of the US Forest Service. Post inventory, once the maps are generated and there's a definitive set of maps, Ray is working, and his team is working on engaging, integrating, and analyzing, and engaging the stakeholders, tribes, cultural perspectives, and integrating socioeconomic science to be able to assess the level of threat using different threat layers. There's a conceptual diagram on the right of what those threat layers might look like that would be produced independently and overlaid on maps of mature and old growth to assess the degree to which the exposure for risk or threat is high or low for certain areas. And then that could influence policy in terms of management and monitoring more effectively. I'd like to thank the MOG team, GEDI MOG team, NASA, UMD, and Harvard Forest, and also the number of US Forest Service colleagues that are working hard and working with us. And we are effectively supporting them in their efforts to generate more definitive maps for policy. and management for the Forest Service. And with that, I'll take questions. I haven't looked at the chat, but yeah, thank you.
Excellent. Thank you, Dr. Kai. This is Peter Falcon. I'm going to be doing the Q&A portion. So we actually do have quite a bit of questions in the chat box. I'm going to go ahead and read them to you, and hopefully you can provide us some answers. So the first one is basically, let's see. As old growth forests are disappearing rapidly around the world, is it a good strategy to focus on maintaining these forests? That's one question. And the follow-up is, what strategy would you suggest for new forests in the future?
Yeah, I mean, I think it really goes down to, it's a values question of why protecting old growth. You know, it really is a societal question that necessitates input from different value systems. I like old growth. I like seeing big trees, right? This is something that I grew up doing, and I've done, and I've enjoyed those types of encounters. But they also have lots of carbon, right? And they're able to store it, and it's a storage mechanism that's stable. And so I think it's worthwhile to protect. There's a lot of biodiversity hotspots in old growth that are unique to old growth systems. And I think globally, I think there can be a perspective of a portfolio approach, right? Like some old growth is going to be naturally reset to young, and some young and intermediate forests are going to progress naturally to old growth, right? And they're going to have the characteristics and the benefits that would be provided by the existing old growth. So it takes a bit of management of the different demographic stages of the forest and having that recognition on the front of the mind, I think.
Thank you. And of course, speaking of carbon, of course, we're going to have questions on trees and carbon. So the next question is, are old growth forests better at mitigating climate change through carbon storage than younger forests?
My personal question is, they're there, and old growth forests have the carbon stored, right? They've done their job effectively from a carbon perspective. If you lose that, it's going to take 100+ years to get another plot of land to have the same benefit, right? Younger forests take up more carbon in terms of rate of accumulation. They're growing faster. There's more light. There's more space and nutrients. And so I think you should protect what you have and focus on building up the stores in other areas.
Gotcha. Another question is, what do you consider the greatest risk for old growth forests?
I don't think we've nailed that down yet. I mean, land use and land management is one, identifying where they are, where those plots of land are, and doing our best to protect them. You know, in the West, it's fire also. We've seen fires in Olympic Peninsula that haven't happened, and fires in the last few years. So that's not typical of the system, and just being able to recognize where the risks are and how they are regionally dependent or system dependent is a task that we're working on.
Gotcha. And a few slides back, you had showed us something called FIA data. What exactly is FIA data?
It's the Forest Inventory and Analysis Program. It's the U.S. Forest Service. It's a plot network of ground-based plots where someone goes out there and they resample. They'll take tape measures, and they'll take diameters of trees. They'll measure branch fall. There are packages that you can process and download these data. It is a very large and extensive data set. But in forest ecology, it's really there's no analog in the globe. It's there are other countries that have networks, but this one is pretty expansive. I think there's 300,000 plots plus, 100,000 in forested federal lands. So it's pretty expansive plot network of ground-based measurements across below ground, above ground. Yeah.
Thank you. Last two questions. Are you just focusing on the US, or do you have a focus area outside the US that you're studying as well?
We'll eventually extend it to globe. I'm an ecologist and also a global ecosystem modeler. This is what we naturally think about in our group, but it is an executive order, and the executive order is for the US. Right now, we're focusing on CONUS, but we'll extend that analysis to Alaska as well, and the other territories, including Hawaii, of course, which is a state. But yeah, right now it's just the US proper.
Gotcha. Okay. And a last question. So with the GLOBE program, we have a lot of students and citizen scientists that go outside, the urban areas, suburban forests, and make tree height measurements. Is there any way for them to visually kind of ID the difference between an old growth forest and a younger forest?
Yeah, I mean, what is a forest, right? I think it's not a pixel at 25 meters squared, right? And I don't think so, right? Right now, the maps themselves that have been generated by the Forest Service in terms of maternal growth are strictly on federally managed lands. There is no, to my awareness, there's not a data set that can pinpoint tree in particular. We are working with a group with Jim Tucker at NASA that's using Maxar data, radar data, to get individual trees and individual tree heights that are going to help us inform a tree-based identification of height status that will, in some ways or another, try to integrate into this classification maternal growth state, if that helps.
Thank you, Dr. Gaia. Thank you very much, and thank you, Ben, as well. I know you both put the slides together. So once again, thank you very much for your time. Thank you for presenting to us. As Brian mentioned, this is really an international collaboration of our partners here. So we have questions from all over the world coming in. So once again, thank you very much for your time.
Thank you for having me.
All right, Brian, I'll turn it back over to you.
All right, thank you so much. Yeah, thank you, Dr. Kai, for that amazing presentation, and the great answers to the questions as well. Because we heard several years ago from one of the forest researchers in Congaree National Forest. I believe it's an old growth forest. So he talked a lot about that, but that was several years ago. So this is one, a great refresher, and two, lots of new knowledge for all of us with this campaign. So, thank you so much for the presentation and, agreeing to do it, especially on a Friday afternoon. So thank you so much for that. So right now, I'm going to pass it over to our own Peder Nelson. And as you know, Peder Nelson is the data guru for our campaign and also the land cover science lead for the Globe Observer. So let me go ahead and pass it over to you, Peder.
Hey, thanks, Brian. While we were getting that wonderful presentation, for me, this is sort of what brought me to the Globe program, actually, is this idea that, hey, it's wonderful that the Forest Service is doing all of this data collection. They have these professional networks. They have, this sample of data out there that they've been collecting for a really long period of time that allows them to do analysis just of their plot data. And that is almost exactly what the Globe program has set up. And I think one of the big differences is when the forest inventory data is being collected out in the field, they're not just making a tree height measurement. They are actually inventorying every single tree or shrub or grass, and in some cases, even the lichens and mushrooms, and they're really getting detailed about that particular location. This is exactly like our site that we're asking you to identify within the GLOBE program and to do the same level of detail. But it takes a lot of time, and that was alluded to earlier. And I think we also have that problem in our campaign where we don't have enough time to collect all of the information that's needed to actually make the estimates of carbon. You need more than just that tree height. You need the diameter of that tree. You also need to know what type of tree that is. You need to understand how wide of a canopy spread that is. So, we bring in scientists who are demonstrating the value of very detailed information. And I think that's a really relevant part because it shows the potential of the GLOBE program to complement professional Forest Service and other countries who are doing similar sort of inventories. And many countries have a similar sort of inventory technique. Now, the key is it's a sample, right? So that's where we can actually get in between those sample locations to see how some of the data that is being produced, that we saw earlier, actually works in our area. And to me, I think one of the things that I did is I changed my my profile picture to one of the areas in Oregon that has really high biomass or really a lot of carbon. And I hope that you can kind of see what it looks like in that type of place. And so this is an example of a high biomass or a high carbon area, a location that actually has really tall trees. And I would venture to say it's very likely that as you try to track that LiDAR beam through the canopy of the forest all the way down to the ground where I'm at, you actually you see that structure that Dr. Cowell was talking about in terms of how tall are those trees. Look at all the ferns, all of the understory trees that are there, in addition to what is measured at the very top of the tree. So I want to really emphasize that our Globe Observer land cover photos, in addition to those tree height measurements, allow us to really get at the understory of the forests. And this is the part that tends to have all of the biomass that has been accumulated over year after year after year after decade after century after century. These places very unique, and also most likely places where you are not living. Okay, so rarely will you be doing an urban inventory of old growth forests when you are actually living right there. There are some examples where that's not the case, where people have kept the land use of some areas forested. So you might have 200 or 300-year-old trees there that might have, and you might be able to see what it looks like on the ground and be able to describe it. But I'd say, by and large, it's a different technique. And this is something that I want to highlight, that definitions matter. Okay, so we were talking about this, and we've really thrown around this idea of mature, old growth. What the heck are those things? And I want to take us all back that we have definitions in the GLOBE program here that do rely upon some information that help us to break up our landscapes. And so, pay attention to your elevation, and pay attention to where you might actually find that old growth, because this is not the first time that this map has been made of where old growth or where trees are located in the world, right? The GLOBE program has been doing this for a really long time. So as we think about our definition of trees, within the GLOBE program, There's the closed forest trees, there's the openly spaced trees, there's the savannas, and all of that gets into some of the density that we can actually see on the ground when we are doing our observations of our land cover. And I want to highlight, rarely will you ever be able to do a tree height measurement or estimate in a high carbon area. You're just going to be, you're not going to be able to see the base of the tree, like my photo here. You're not going to be able to walk evenly across there. And so those are locations where it's going to be really challenging for us to actually create and measure those tree heights. The way that the professionals do it, they go out with the tape measures. They go out with lasers. They do some of those things because you cannot walk in the way that Brian and the ISAT-2 team has set up the Globe Observer tree height estimate and the requirements there. So I want to emphasize that point that, in fact, we might be missing data in terms of our tree height in these mature and old growth locations. So that's where you really need to switch protocols to the Globe Observer land cover and show us what that area is like, how it's hard to actually navigate around because of all the biomass that is not only standing upright, but is also fallen over on the ground and is going through its, that part of the carbon cycle. Okay, so I really want to emphasize definitions as being a really important part. The other thing that I want to really emphasize to us is that we're not the first ones looking at this question and at this problem. And so, I really, as we talk about the age of trees or the height of trees, recognize that there's been a lot of research around these questions. And I'm bringing up, this research that came from the area that I'm in, both at my Globe partnership, but also where some of the highest carbon measurements that have been made in the world come from. And that is the Pacific Northwest, where our moon tree is actually the Douglas fir that was planted at, in Oregon at our location for our Globe partnership. So this idea of measuring a tree over time and looking at its response to climate is something that is foundational to our Globe partnership. But I want to emphasize that to do this, it requires dedication to collecting ground data. Finally, I want to say that there's a lot of definitions out there beyond what the Globe program has put forth. And it's really, really important to get on the same page and to be very precise about a definition, right? Because that is what we are using to label our spectral information, our photos, and what it actually looks like in our location. And I thought that was a really important piece, that old growth and mature forests will look different in different locations. And so I'm hoping that, over the course of this year 6, we'll actually be able to see different estimates of carbon, not only from these measurements that are being made by scientists, but also what it looks like on the ground. Because I think one of the things that I notice when I'm looking on the ground in old growth forest is I can actually sometimes see things like fire effects, or I might see all those lichens like is in my profile picture right now. But I want to emphasize that definitions are the way that we drive the science conversation, okay? And I'm bringing this up because, as was highlighted, this is an executive order, not only in the United States, but it's really something every country is trying to get a handle on, where their carbon is naturally held in these forested landscapes. And again, to understand a forest, you need to first not only make one individual tree height measurement, but you then need to turn to the next trees that are around it and also make those repeat measurements. And so you can see that in this landscape here, this old growth ponderosa pine forest, we'd have a much better chance of being able to see the top of the tree and also the bottom of the tree. And so we might have a better luck of being able to add a tree height estimate using Globe Observer to these locations, right? I would also say, if you included use Globe Observer and included the cloud and did that estimate, notice you could actually see some of the trees or some of the sky cover through this, and that gap in the forest and trees is an indication and something unique to these types of forests. They actually start brightening up again when they start getting older. And so it's not only that they're green, but it's the spacing of the trees and those colors that we can see and capture on the ground that helps with our definition of what an old growth or old trees look like in our location. So, you know, these are things that, yes, are specific to our particular country of the United States, but I guarantee that you will find similar definitions for any country that is part of the GLOBE program. Okay. And I want to, you know, show you that when you go into all of this data that's being collected, not only is it useful for you know, people who are managing and being stewards of this land, like the U.S. Forest Service or the forest agency in your country. But I want to highlight that I went out and I was able to follow a road that goes up in elevation. And so I was able to see the difference between trees and the carbon in a low area. And as I went up in elevation, I was able to see the age of the tree and the structure of that area change, and be able to do that just with my Globe Observer land cover photos. And I want to highlight, you know, these upward photos that we're getting from the land cover tool and also the clouds observations are, you know, both really helpful to us to be able to describe the spacing of that canopy, which goes into the definitions of whether this is a closed forest or whether it's an open forest. And then we can start talking about the height of those trees and how the sunlight might be interacting with and helping to help the mosses and the lichens and some of those other things that are growing on the trunks of the tree that give us those carbon measurements that are beyond just the tree height, right? And just those trees. Because here, as we're looking up, it's really shaded, but there's mosses, and there can be tons of mosses that are on these trees that we see on the ground and that are being recorded by the satellite measurements coming from the International Space Station or our sensors like GEDI and Landsat. And I want to quickly go over, because this is something that I've been involved with for over 20 years. And we've been actually taking those same forest inventory plot data and putting it together with our Landsat data to give us a wall-to-wall map, as we say, across the United States, you know, that should give us an estimate of how much megagrams of per hectare of carbon is in that area. And so if I just I want to zoom in on this area that is my GLOBE partnership region in the state of Oregon. One of the things that we do start to see as we zoom in is the changes, and we can actually see the difference in estimated carbon, and you know, based on who owns the land. And so here we can actually see hard edges and lines that show us that there are some areas that have a lot less carbon, and then you see these blue areas that have a lot more carbon. And the nice thing about what scientists like Dr. Calle is doing here is we can now click on a location and I can get a map that gives me a number that estimates back in the year 1990, there was around, oh, my cursor's in the way, 363 megatons of per hectare of biomass there. So biomass, an estimate of carbon there. But you can see it's relatively stable and flat. It is still possibly gaining or losing. We're really unsure at that particular location. But it's staying relatively flat compared to a different area, like a yellow area here, where we can actually see a change in those carbon estimates that are coming from our ground measurements. And we're using the satellite data to try to make these estimates consistent across space, across geography, as well as in time. So why did this big drop occur in this particular year of 2009 to 2010? And how tall are these trees in this location? This is what we're trying to provide to you in this upcoming year, is not just, that there's trees there, but we can actually turn it into numbers of that give us estimates of carbon. And therefore we can look at how our choices, or how maybe the change from one stage of age might impact things like our biomass and our regrowth in some of these areas. And it's really kind of exciting to be able to now go around the world and not just get an idea of that there's a tree in that location, but to start to be able to put biophysical numbers or numbers to it, so that it's not just, this simple map like what we're asking you to do, which is, hey, there's trees here. That's useful. That gives us some information, but it's really moving into, okay, can we use that to tell us how much canopy cover is there? And so we can estimate that. And then we can also then turn it into these carbon numbers. And all that really does go back to our definitions and these numbers that come from very detailed ground measurements, the forest inventory data, or the GLOBE data, and following those GLOBE protocols. And then what I love about this is, let me just zoom in a little bit here so that you can see it. I'm going to read this, because what ends up happening is, after you make these measurements, we then actually turn to some mathematical equations to try to understand and try to describe this. And what I want to highlight here is that scientists spent 14 years trying to measure enough trees to get a consistent set of measurements of 14,000 trees to understand and make some of their models with. Okay, so that's what, the amount of time that it actually takes to be able to provide, numbers to Dr. Calle and others like him, and people I work with, to be able to make these estimates based off of what we're asking you to do. And I want to highlight here the key information that was collected to come up with these estimates of how much does a tree grow per year. You need to make those detailed measurements of what is that tree species. So you have to identify it. And then you also have to make that measurement of what is the diameter of it at breast height, like Brian's been asking you to do. But you also need to go that extra step of measuring the crown size, right? How big is that tree spread? And then where is the location? Because again, that indicates how much water it gets, or how much sun it gets, or other information that really drives the growth rate. And then also knowing the age, because just like people, trees do slow down as they get older. And so they may not grow as much as they did, when they're 50 years old, as they did when they were 20 years old, or maybe even 10 years old. So we need all of that information to be able to answer the very obvious question that everybody comes to this webinar with is, okay, I have a tree height, I have an estimate of what is the diameter of that tree. Maybe I know what species it is. Then if you have that information, you can go to a place like this that has put together an equation that you can plug those things into, and you can then approximate going forward how tall might that tree be in 5 years. How tall and how much carbon might be in that tree when the GEDI instrument comes back online in 2024, and it is able to make a measurement of that same tree. Are your numbers going to align? So, one of the things that I'll highlight is this is what a lot of scientists spend their time doing, and we then work together to share our metadata with each other. So we share our definitions, and then we start to put together and share our maps together with other people. And so I will actually share this story map with us so that you can explore it on your own, because it does get into what is the definition of an old growth tree, and what are the benefits. How might you use this to understand your own community, right? So this idea right here of age and these groupings are really important. And so you can explore this type of story map to understand where those things are located. And I'm going to go down to explore the data at the bottom, because what that allows us to do is actually zoom into your location, and you can see where your closest mature and old growth forests are located. And so I'm going to just kind of zoom in, and you'll see some blockiness, some things like that. But to bring us back where we've been pointed today, you can actually see this is how they're sort of grouping some of these things. You have to explore it to understand what these colors mean, because that's part of map reading. But there is this information available to you. And it would be really wonderful to ask the question of, why is there old growth in these locations and not in my location here where I'm doing my own measurements? And that might go back to that ownership question, like we were talking about earlier, but it might also be some other decisions that were being made. So there's that whole why are things looking the way they are question that I think is really important. Okay, so I'm going to end here by highlighting the moon tree that I have at Oregon State University, because a lot of our old growth trees that I was showing you and biomass that I was showing you earlier on those maps are actually Douglas fir trees. These trees are really long-lived species that are needle leaf, evergreen, and they also have a very widespread distribution. Here, I want to point out that our tree is right by a building that got and so it may not be representative of everywhere that's out there. But I'm going to stop my presentation here with how important these ground photos are, because we've had some conversations about people actually, I'm sorry about that, about people going out and doing stewardship, planting trees, doing some of those kinds of things. If we're able to date those, here we actually have a relative height of that seedling of this moon tree when it was planted, about knee height. So we can estimate that's maybe 1 meter tall, 3 feet. That gives us an estimate of that height. Well, oops, sorry about that. Here we now can see in 2010, this is how tall that tree is. I don't know. If we had some people stand next to it, we could have a reference. I have actually gone out and remeasured this tree, but you can see how just having these photos of trees on the ground over their course of their lifetime can help us to start to understand the satellite imagery and some of the data that's coming out, even to be able to answer that question that you had very early on there, Peter Falcon, which is, what is the definition of an old tree in my community? And what's the difference between a single tree that might be really old versus an area and a group of trees that might be really old, right? And this age is one that we always get asked about. So I encourage you to start thinking about this relationship between height and age, and thinking about, well, what might keep something from still growing and getting taller. And I just want to highlight that I'm really excited about using this because back in 2010 or 2012, there were some other people that had flown an airplane and they had collected LiDAR data similar to that GEDI data, that height data, that ISAT-2 data, but it was done over our moon tree. So I actually have an estimate in 2012 that tells me how tall that tree was at that year. So what I really appreciate about all of these data sets that are available to us now is that we can actually start putting ourselves on this timeline and checking our measurements and recognizing that some other people have been paying attention and measuring when maybe we haven't. And if you're going to be one of those groups that are lucky enough to get an Artemis seedling, when you plant that, you are setting the record for how tall that tree was at that moment, and potentially what is the rate of growth in 5-10 years of age, as well as how much carbon is it actually absorbing. So I hope that you got excited about this really important emphasis on two ends of the spectrum. You have the very young trees that are getting planted with Artemis and that went out into space, and what is their life going to be like? Then you have these moon trees that were planted in 1976 approximately, who also went to space. What did they experience? And then you have these mature and old growth trees that have been on Earth for hundreds of years, who've been photosynthesizing and interacting with the sunlight and the people around them for a really long time. And is there a difference in the way those things grow? That's part of our science questions that I'm excited to explore in year 6 of our Trees Around the Globe student research campaign. Brian, wrap us up.
Hey, Peter, this is Peter Falcon. We have 2 questions for you. I know we don't have too much time, but we do have some questions hopefully you can answer.
Yes.
I know you can answer. The first one is, how often do you recommend taking a land cover observation at the same time a tree height observation is taken?
Yeah, so I like to do that every single time. And the reason why is because then I'm able to actually get a little bit of the differences in the leaf color. So I'm actually getting some phenology piece for the green up, green down. And one of the things too is that by doing those repeat observations between land cover and tree height, we actually have 2 location numbers, and we can sort of compare those 2 things right there, and better locate ourselves. And because this is something I highlighted early on, that is one of those challenges between measuring with a laser above and trying to locate ourselves underneath the canopy of the tree, is we get interference right in that area. And so the more measurements we have on the ground, the more observations we have on the ground, the more likely we are going to have confidence in our placing ourselves on the world. And then the GEDI team, the ISAT-2 team, all of these science data coming from NASA is also going through that same process to make sure that we're talking about the same place on Earth. And so by doing those 2 things together kind of consistently, we're able to really gain confidence in our location, but then we're able to get some fun things like the shadow length changes throughout the year. That sun illumination, that is something that we can use to also estimate our height. So to me, I really tie those things together between, especially when I'm estimating, I start off and I do my tree height, do my all of those kinds of things. But then when I walk to the bottom of the tree, like this moon tree here, I walk to the base of it, and I did a land cover observation there so that we could see what the canopy architecture looked like. And knowing that this tree has branches going all the way down to the bottom will give us a different carbon number than if the tree branches only went down halfway. So it's amazing how those little details actually get into how accurate are we with our carbon numbers, right? So if the more of those observations you can make, the more confident that you can be about your numbers. And then when we pass them off as even just a spot check to Dr. Calle and his team, they'll look at that and go, oh, okay, that seems to make sense with our model and our estimate for that location. Or, oh my gosh, it's estimating 350 carbon or million tons of carbon in this location, but it's clearly a grass field. That doesn't line up, right? And so that ground photo is just a great way that we can even provide a spot check as other groups are looking to understand and describe our locations. So I hope that we'll in our upcoming webinar talk about those climate numbers, how we think about trees as part of that climate system, that carbon system, and how important it is to do these observations whenever we can, as rapidly as we can, so that we can get those changes over time.
Gotcha. Thanks, Peter. Last question. And I do want to point out that Brian put in the chat box your story map for the moon tree. And thank you for putting the story map for the old growth trees as well, old growth forest. That's awesome. So last question, let me put my reading glasses here, and you may have answered this already, but is it more difficult to take tree height observation in an old growth forest compared to a young forest?
Ooh, I would say, okay, so this is a really fun one that what I like to do is I like to go onto any one of the mapping programs, even the Viz system, and turn on that satellite view. Because when you turn on that satellite view, you will actually sort of see the shadow of these tall trees, and you'll see this really interesting pattern that demonstrates kind of this old growth piece of things. And what you notice is that the tree spacing in old growth tends to actually start opening up, and you can see the sky view, and you can actually do a cloud observation even inside of them. And you also will find dead trees that are standing and that actually brighten up that area. So that tends to be a characteristic of really old growth forest, especially where I'm located. Now, in some places, it might be a little bit different, but by and large, that spacing of the trees tends to open up, especially after a certain amount of age, 200 years or so in our case. So between 50 years of age and about 200 years of age, when a forest, especially in our area, it goes through this really dense area where you cannot actually see very far. So our ground photo is obstructed. You cannot actually see very far until those trees start falling over, opening up space, and we get these canopy gaps. And those canopy gaps what allow young trees to get in and actually start to add that interesting structure that is a characteristic of old growth and mature trees. That's something that when you plant trees, we recognize that they're not all going to live. And we hope that they will fall over, they will decompose, they will become part of the soil. But that takes a long time. And so you'll find that those young trees, those young forests are the ones that you cannot walk through. You cannot get through very easily. And so those tend to be the ones around us as well. So it's a really interesting and obvious way that you can start to understand and think about the age of those trees and how far can you see. And you're lucky when those old growth forests, because that's when you can see those individual tree trunks that are characteristic of like of a redwood forest or our giant sequoia forest up in the coastal California. But when we start actually going back to our tropical forests, again, this is where how far can you see is kind of a very quick way that you can say there's a lot of carbon here. And so that's where you're doing a very quick, rapid assessment of carbon by those land cover observations. And even by indicating, I can't do a tree height here because I can't see the top of the tree because they're so darn close, right? So Peter, to me, this is one of those parts where we know that we're not going to get tree height everywhere, but we should be able to get Globe Observer land cover photos to help us to understand the understory everywhere.
Gotcha. Thank you, Peter. Thank you once again for a very, excuse me, energetic presentation as always. We love hearing from you. So with that, once again, thank you. I'm going to turn over to Brian so you can finish us off as Peter mentioned earlier. Take us home, I think it was.
All right, awesome. Yeah, thank you, Peter. And Peter. But one thing I noticed that this is a great segue to what's going to happen in year 6, because all day today we talked about the union of the data with the U.S. Forest Service and the Old Growth Forest Research with GEDI, talking about that old growth forest versus the younger forest, talking about when you can't take a tree height observation, maybe because you can't see the bottom and the top of the tree, do the land cover observation. So it's a combination of, the importance of knowing when to do a tree height, when to do a land cover, and when to do both, and with which, I like your answer with that, Peter, is that try to do it every time, because we want to know what the environment's like around you. We want to know what maybe the understory looks like. We want to know what the ground surface looks like. And, when you do with everything with the Globe Observer, you do answer those kind of generic environmental questions, if it's raining, if it's snowing, if it's dry ground, if it's muddy, things like that. But that land cover, of course, will tell you more. What, granted, the simple land cover observation, you do the 6 photos, and then, but to get that really detailed thing that we're looking for, with this data is the analysis of the land cover, which is super important. And we know it takes a little longer to do than the simplified one, but just think of the amazing amount of data that is going to be in the Globe database with that information. So I'm going to end it with just a reminder of our next campaign webinar, and that's going to be the State of Trees, October 2023, and that will be the start of year 6. We will be focusing on the YCC, the Globe Year of Climate and Carbon, and we will. This will be back to a Tuesday schedule again for this webinar, and this will be at 1 o'clock Eastern Time, 5 o'clock UTC, 7 p.m. Central European Standard Time. So we will see you all there, and you will get all this information sent to you. I will send this invite out for this webinar to all the campaign participants right after we adjourn with this webinar. But then also, stay tuned to the campaign website, because we will be updating that, within this month to get prepared for year 6, which begins on 1 October. So, but thank you everyone for being here, and have a great weekend, and we'll talk to you soon. Bye, everyone.